Hello, welcome to this mathematics tutorial series, which is organized by Oromia Education Bureau. I am Dr. Garuma Abdisa, and our today's topic is about spatial limits. In the other tutorial, I have introduced to you the importance of limits and how they always affect our lives, especially in every field of science. There is always a concept of limit on the one side or on the other. And the building block of the problems of derivatives and that of differential calculus is entirely based on the concept of limits. So without talking about limits, it is quite impossible to talk about derivatives. So I will try to make attention on some of the spatial limits, not on the whole limit itself, because these what are called spatial limits are spatial in the sense that these spatial limits are spatial in the sense that they become building blocks for derivatives and consequently for integral calculus. So we have five spatial limits, one of which is the limit of sine x over x as x approaches to 0, which is 1, and the second spatial limit is the limit of 1 minus cosine of theta over theta as theta approaches to 0 is 0. I will derive for you later on, or I will geometrically show you how these spatial limits could have their values to be like that. But for now, I want to introduce to you these spatial limits first. The third spatial limit is the limit of 1 plus 1 over x, the whole the power of x as x approaches to infinity, which is e. This e is an irrational number which is 2.718 to 818 to 8, but it doesn't keep going on like to 818 to 8. The other digits coming after the other are not like that. It is an irrational number. What follows is different. It doesn't repeat itself. So that is the value of this spatial limit. How could it be like that? I will show you later on. The fourth one is the limit of 1 plus y to the power of 1 over y is also e, where e is that same e. So 3 and 4 are roughly the same, but with different expressions. And the fifth spatial limit is the limit of a to the power h minus 1 over h as h approaches to 0, which is ln of a, the natural logarithm of a, where a is greater than 0 and a is different from 1. So if you are new for derivatives, you have to get started first by being introduced to these five spatial limits. These five spatial limits are, as we have said, are building blocks of the problems of derivatives, and are so important that they are called spatial in this sense. So from now on, I want to one by one show you how these spatial limits value could be determined. The easiest way is to demonstrate that the limit of sine of x over x as x approaches to 0 is equal to 1. For those of you who have a background on how problems of limits are done, this could also be demonstrated using what is called the squeezing theorem of limits. But in this case, to make life much simpler, I have a very different approach, geometric approach, which is pretty simpler, especially for beginners to understand why this limit has to approach to 1 when the argument of sine becomes too small. Assume this is a unit circle having a radius of 1, and if this is y, that is this line is y, sine of theta is always opposite side divided by the hypotenuse side, which is y divided by 1. So y over 1 is simply y. So what is y? Y is simply sine of theta. So this blue line from here to there is simply sine of theta. I wrote it here, that is sine of theta. The same applies for the second half of the blue line, that is also sine of theta. So the whole blue line from this to there, I mean this green line from here to there, is twice of sine of theta. and the curve, that is the blue line from the outside blue line from here to there, that is a curve from outside, that is theta, because it is subtending this central angle. And also for this one, that is also theta. So this curve is theta, that is theta. Theta plus theta is twice of theta. When 2 cancels 2, I'm left with sine of theta over theta. It is quite natural to think that when this angle becomes smaller and smaller, for example, if I make the angle to be a little larger, this curve and this straight line are a little further away from each other. But if I make the angle to be smaller, this curve and the straight line now would tend to overlap. So as you make the angle sufficiently small, the green line and the blue outer line, that is the curve, would be almost same. So we take that as a principle that shorter piece of curve is nearly straight. A shorter piece of curve is nearly straight. Means, for example, the blue outside curve and the straight line here are almost the same. Means their ratio, that is sine theta for this one and theta for the other one, would be same. So their ratio would be 1. That is the way we derive limit of sine x over x. At least we'll be able to demonstrate that this special limit is 1. Now the second special limit is the limit of 1 minus cosine of theta over theta as theta approaches to 0. And in this case, this red curve is a part of a very big circle. You can assume as having a very wider circle, and this is a sector of it, and this is an angle theta. And now I want to take up to here, up to this point alone, and it makes a 90 degrees there. And then if I say this is x, cosine of this angle theta is the adjacent divided by hypotenuse. So cosine of theta is the adjacent x divided by hypotenuse is 1, because it is a unit circle again. So that is simply x. So from here to there is just x. And the same applies for the lower one. But I want to know now the gap. From here up to the end, that is up to the red curve, it's the radius, the same as the radius is 1, and up to the blue straight line, it is x, that is already cosine of theta. So the gap between this and that is simply 1 minus cosine of theta, that is the gap. As the angle becomes sufficiently small, that gap tends to 0. So the gap, this part is the gap divided by theta, that is the curve approaches to 0 when you diminish the angle. That is essentially what is meant by this limit. So the limit of 1 minus cosine theta over theta is always simply equal to 0. Now we come to this special limit of 1 plus 1 over n, the power of n as n approaches to infinity. This is one of the remarkable achievements in mathematics, because the problems of logarithms, exponential functions, and so on are based on this special limit. E, especially the base of the natural logarithm, is e. It's much better to convert this limit into logarithm first. So if I let this limit to be equal to some, say, y, and then what I should do is I will take ln of this y. I will let this limit of 1 plus 1 over n to the power n be equal to y. So ln of y, I'm taking the natural logarithm of either side, both the left and the right side. I'm also taking the natural logarithm of the right side, and then what happens is it becomes equal to the limit of n times ln of 1 plus 1 over n. As you know, for any logarithm of a to the power k to the base anything, whatever, is equal to k times the logarithm of a. The power can be taken as a coefficient. That's one of the properties of a logarithm. With the same argument, because this is an exponent, I took it to the coefficient here. So we can rewrite this expression in this way. Now I want you to let delta x be equal to 1 over n. In this case, our limit is in terms of n approaches to infinity. I wanted to substitute 1 over n by delta x. Because n is approaching to infinity, 1 over infinity, which we have replaced by delta x, now should approach to 0. So the limit of n times ln of 1 plus 1 over n, that is originally our this one problem, is now replaced by limit of, instead of n, I can write n, if delta x is 1 over n, n is also 1 over delta x. So instead of this n, I can write 1 over delta x, ln of, there is 1 here, instead of 1 over n, because 1 over n is already delta x, I will substitute that by delta x. But I'm just subtracting minus ln of 1 here, because ln of 1 is simply 0, and subtracting 0 from something doesn't make a difference. So, but we have this definition of limits. F derivative of x, that is what is called the derivative of any function, which is the limit of f of x plus delta x minus f of x over delta x as delta x approaches to 0. If I now consider my x to be 1 and my delta x to be delta x here, that is the same as having the first derivative of ln of a function, because this is exactly the same as this one if that one were x. So this is d by dx of ln of x, which is simply 1 over x evaluated at x is equal to 1. So 1 over 1 is simply equal to 1. So I started with y, which is this one, but now I did a limit not for y itself, but rather for ln of y. So what I should do is, finally, I will take e to the power of ln of y. E to the power of ln of y is simply y. That is my original problem. Now e to the power of my final answer, that is 1. E to the power of 1 is simply equal to e. That is the way we derive this formula. And try to exercise by yourself so until you will be able to manage deriving this special limit by yourself. That is the fourth special limit, which is pretty simpler to derive, because it is just change of variable, and it is exactly the same as the first limit, but in its form this way will also help us to tackle some problems. That's why still we are able to consider it as a special limit, even if with only a change of variable with the third special limit, that we are able to write this special limit in a different way. We have already shown that the limit of 1 plus 1 over x, the whole to the power of x, is equal to e. And then now I want to make a substitution that y is equal to 1 over x, where as x approaches to infinity in this case, because y is now redefined to be 1 over x, so that is in turn equal to 1 over infinity. So x approaches to infinity means y must be approached to 0. That is because 1 over infinity is approaching to 0. So by directly substituting everything I have, instead of x approach to infinity, I will substitute now with my new variable in terms of y approaches to 0. This is 1 plus y, because 1 plus 1 over x is already substituted by y, so that is 1 plus y. And instead of x, if y is 1 over x, it also implies that x is also 1 over y. So instead of this x, I can write 1 over y there. So that is simply the way we write this special limit. It must be equal to e, because we didn't do anything to the function except we have simply changed the variable. We have changed everything from variable x to variable y, and a change of variable alone doesn't affect the functional value, as any of those variables approach to what they correspond to, in case of y to 0 and in case of x to infinity. So it makes sense that this special limit must also be e. The fifth and the final special limit we have is the limit of a to the power h minus 1 over h as h approaches to 0. And this kind of special limit is very important in order to do some logarithmic and exponential functions, the derivative of them. And in order to evaluate this limit, I want you to substitute a to the power of h minus 1 by x. So if I write a to the power of h is equal to a to the power of h minus 1 is x. If I write a to the power of h minus 1 is x, I can also write a to the power of h is 1 plus x. So from this one alone, I can write h. I will take the natural logarithm of either side, natural logarithm of a to the power h, and the natural logarithm of this side. Then I can directly write it this way. And h is ln of 1 plus x divided by ln a. I'm simply dividing by this term to eliminate and remain h alone over here. And from the relationship a to the power of h minus 1 is x, we can write that as h approaches to 0, because any number to the power of 0 is 1 and 1 minus 1 is 0, x must be approaching to 0. Let us find the limit of the reciprocal of our original problem instead of the problem itself, because that will make life much simpler than if we were to do the original problem by itself. So I'm originally asked to find the limit of a to the power of h minus 1 over h as h approaches to 0, but rather I want to find the limit of the reciprocal of this, that is h over a to the power of h minus 1. When I find a certain value for this one, my final answer would be the reciprocal of my answer for this one, so that it would be an answer for my original problem. So let us now proceed with calculation of the limit for this reciprocal of my original problem. So that is the limit of, here I have a to the power of h minus 1 on the denominator side, that is a to the power of h minus 1 is this one. So it is on the denominator, means I have to make it 1 over x here, and h is equal to ln of 1 plus x over ln a, that is ln of 1 plus x over ln a here. And because 1 over ln a can be taken outside of the limit, because our limiting variable is x instead of a, so that I can write ln of 1 plus x. In logarithms, if you remember, logarithm of a to the power of k is same as k times logarithm of a. That power can be taken to be the coefficient, or you can also go from here to there. In either way, the mathematics is consistent. So now I wanted to replace this 1 over x back into the power here, so that I can write this 1 over x being back to the power over there. So the term in this square bracket that you see is very similar to my third special limit, that is the limit of 1 plus y, the whole power of 1 over y as y approaches to 0. That was the fourth special limit, that is actually this one, the limit of 1 plus y, the whole power of 1 over y as y approaches to 0. Now the same, which we have said that it has to be e, is now reappearing in this ln argument, ln of 1 plus x, the whole power of 1 over x as x approaches to 0. So that must be e by itself. So the term in the square bracket must be e. So 1 over ln a, this one, times ln of e, but ln of e is, ln is simply a natural logarithm, so logarithm of e to the base itself. So that is 1 over ln a is 1 over ln a. Originally my problem was this one, but I rather did the limit for the reciprocal of it. So the answer for this one must be the reciprocal of my final answer here. So this is the answer for this one. So as a summary, we can deduce that the first special limit, limit of sine x over x, has some link with this one, because once we are given this one with some mathematical arguments, we can derive this one from this one. So that one is dependent on this one. And these two are dependent on this one in some way, because during our derivations I've showed you. So these 5 special limits can actually be reduced to only these 2, but for the sake of convenience we will keep 5 of them because they are so much important to pave a way for the development of derivatives. And this brings us to the end of this lesson. Thank you very much. Have your own time to practice by yourself.